Good morning, everyone. Myself, Dr. D. Anu, Assistant Professor, PG and Research Department of Chemistry, Sri Sharda College for Women, Autonomous, Salem 16. Today, I am going to discuss about acid-base indicators and theories of acid-base indicators. Before going to enter into the topic, let's discuss what is an acid-base indicators. In an acid-base titration, the base solution can be added gradually from the burette into the acid solution contained in a conical flask. When the amount of base added equals to the amount of acid in the flask, the equivalence or end point will reach. The end point of the titration is shown by the color change of the indicator previously added to the acid solution in the conical flask. It's known as an acid-base indicator. There are two common examples of acid-base indicators are phenolphthalein and methyl orange. The phenolphthalein is pink in base solution and colorless in acid solution. Thus, when added to the acid solution in a flask, it shows no color. As added in base, it slightly excess, it becomes pink in color. Thus, phenolphthalein signals the end point by color change from colorless to pink. Similarly, in case of methyl orange, the end point is indicated by the color change from red in acid medium and yellow in base medium. pH range of indicators. Most indicators do not change color at a particular pH. They do so over a range of pH from 2 to 3 units. This is called pH range, which is different from various indicators. The table shows the pH range of some acid-base indicators like methyl orange, methyl red, litmus, bromothymol blue, phenolphthalein. Their pH ranges are given in the table. pH curves and indicator range. During an acid-base titration, the pH of the solution in a conical flask changes with the addition of titrant from the burette. A plot of pH against the volume of solution being added is known as the titration curve or pH curve. For example, the pH curve produced by the titration of HCl with NaOH solution is given in this figure. When adding the sodium hydroxide, the pH of the solution increases slowly at first and then rapidly in the vicinity of the equivalence point. This is the equivalence point, and again slowly. The equivalent point lies between the vertical portion of pH, that is in a neutral pH. The end point of the titration determined by the color change of the indicator in a titration solution. The titration curve shows that it remains vertical around the equivalence point. Similarly, in case of phenolphthalein, litmus and methyl orange may be used as an indicator for acid-base titration. How to choose a suitable indicator for acid-base titration? Acid-base titration depends on the nature of acid and base which involved in the titration. They may be strong acid with a strong base, weak acid with a strong base, strong acid with a weak base, and weak acid with weak base. Let's see one by one. The first one with a strong acid and strong base. Here the strong acid is HCl and the strong base is the sodium hydroxide. We have already discussed that the suitable indicator is one which has a small pH range that falls wholly on the upright of the titration curve. Next, when the sodium hydroxide is added gradually to the NaHCl solution, that is, the strong base is added to the strong acid solution, it shows that the pH titration curve slowly rises and the extreme and in the beginning Then after the equivalent point, the pH dramatically and the curve becomes vertical. Beyond this, the curve becomes almost flat. That shows the slight rise of pH when excess base is added. The vertical portion of the curve extends from pH 3.2 to 10.0 and fairly narrow and fall on the vertical curve. Thus, both methyl orange and phenolphthalein are suitable indicator for strong acid and strong base titration. Next comes the weak acid with strong base. Here, sodium hydroxide is a strong base and acetic acid is a weak acid. The pH curve rises slowly in the beginning, but nearer the end point, the pH changes abruptly from 6 to 11 and the curve becomes vertical. Beyond this, the shape of titration curve is similar to that of strong acid and strong base. Phenolphthalein has a pH range of 8.2 to 10.0 that falls on the vertical part of the titration curve. The pH of the methyl orange lies between 3.2 to 4.4. On the other hand, it does not fall on the vertical curve. Thus, if the methyl orange is used as an indicator, the end point will be reached earlier than the equivalence point. Therefore, weak acid strong base, the titration phenolphthalein is added as an indicator. Titrating the strong acid with weak base. Here, HCl is a strong acid and ammonium hydroxide is a weak base. When ammonium hydroxide is added, the pH of the titration solutions increases gradually. Around the equivalence point, a sharp rise in pH occurs approximately from 3.2 to 8.0. When the curve becomes vertical, the pH range of methyl orange is 3.2 to 4.4 and that of methyl red is 4.4 to 6.0, falls on the vertical portion of the curve. Methyl orange and methyl red are suitable indicator for strong acid with a weak base titration. The vertical part of the curve is beyond for the phenolphthalein, hence only methyl orange and methyl red are used as an indicator. Then titrating against weak acid with weak base. Here the acetic acid and ammonium hydroxide are taken. The pH, when adding ammonium hydroxide to the acetic acid solution, the pH of the titration solutions rises gradually and there is no sharp change in pH around the equivalence point. The vertical portion is missing in the titration curve. Under these conditions, all indicator change color only gradually and no indicator is suitable for weak acid and weak base titration. Next comes the theories of acid-base indicators. An acid-base indicator is an organic substance used for the detection of equivalent point or neutral point in the acid-base titration. An indicator has one color in acid solution and entirely different in base solution. The end point of the titration is shown by color change of the indicator. There are two theories to explain the indicator action in acid-base titration. The first one is the Ostwald theory and next one is the Quinanoy theory. We will discuss with the reference to the two commonly used indicators, methyl orange and phenolphthalein, to explain the theories. The first one is the Ostwald theory. According to this theory, an acid-base indicator is a weak organic acid or a weak organic base. Here, organic acid is indicated by HIN or an organic base is indicated by INOH. The methyl orange and phenolphthalein are both weak acids. The unionized indicator, that is IHIN, has a different color from the INOH minus ions produced by the ionization of indicator in aqueous solution. The degree of ionization of indicator determines the visible color of the indicator solution. How an acid-base indicator works. Let us explain the indicator action by taking methyl orange as an example. Methyl orange is a weak acid and gives the following ionization equilibrium in the solution. When the reaction is carried out, the HIN, which is red color, is converted to H plus when the reaction goes on H plus plus IN minus. This is in equilibrium state. According to the law of mass action, product divided by reactant. So KIN, that is indicator constant, equal to, here the product is H plus and IN minus, and the reactant is HIN. So the product minus reactant, which is according to the law of mass action, the equation has been done. KIN is an dissociation constant of the indicator and it is called indicator constant. If an acid is added to the solution, the hydrogen ion concentration H plus in the equilibrium will increases. To maintain indicator constant, the equilibrium shifts to the left. Thereby, the concentration of IN minus is reduced and the concentration of HIN increases so that the solution is red. On the other hand, upon addition of the base to the solution, H plus ions are removed as H2O by reacting with OH minus ions. This shifts the equilibrium to the right, resulting in the form increase of HIN minus ions that are in yellow color. Thus, the acid solution has unionized HIN molecules predominate and the solution is pink. While in basic solution, iron minus ions are in excess and solution is yellow. Next, indicator action of. Next comes quinonoid theory. The quinonoid theory tells us the cause of color change of an indicator in acid-base solution. It says that an unionized HIN molecules and an anion IN minus or tautomeric form of the indicator, which is an organic dye. The tautomeric form possesses the quinonoid structural unit as called quinonoid form. It has a deep color and it is also called benzenoid form, and this is a quinonoid structure. The color change of the indicator occurs when one tautomeric form is transformed into other due to the change in pH of the solution. Let us illustrate the quinonoid theory by taking example of methyl orange and phenolphthalein. The first comes the methyl orange. Here the red quinonoid form of methyl orange exits in acidic solution and it is converted to yellow form when pH alters to the basic solution. The next is the phenolphthalein. Phenolphthalein exists in two tautomeric form. One is a benzenoid form, which is yellow and present in basic solution, and quinonoid form, which is pink and present in an acid solution. Thank you.